Okay, so I think one thing that most people are going to see when they look at a bolt and they see all those threads cut into the bolt or rolled in the bolt, of course, what they're going to see is, hey, that seems like a giant mess of stress concentrations that is going to make this thing terrible for fatigue. And you know what? You're not wrong. So again, we do have stress razors at the root of every thread. So analysis is fairly simple for this. To be honest, what we do is we've got a number of stress concentration factors that get used, basically based upon a combination of how strong the bolt tends to be. So if we're talking stronger bolts, so yeah, if we're using the SAE grades, 2.2 and below, or 5.8 and below if we're working in metric. Then we use 2.2 if we're using rolled threads, or 2.8 if we're using cut threads. So again, and that's just because the way that the rolled threads work is that they cause the existing grain structure to be formed into place, so it kind of maintains a bit of extra strength there. Whereas the cut threads, they slice through. If we're using harder bolts, so 4 and above or 8.8 and above, then we're working with a stress concentration factor of 3 for the rolled threads and 3.8 for the cut threads, which is fairly high. And of course, we need to figure out what our strength is, our SN. So again, most everything else is going to just kind of be calculated based upon the way we know. So we calculate our SN prime the same way. For load factor, again, we are loading our bolts in tension. If that's not what's going on there, then you're loading your bolts wrong. So we're going to be using the CL of 0.9. Gradient factor, again, that's just based upon what our nominal diameter of the bolt is. So the D that we use here, this is from the table 8.1 in juveniles. So if the nominal diameter of our bolt is, say, half an inch, it's a half-inch bolt, and we're working in this range. So it's reasonable to kind of it gives a range. It's reasonable to kind of extrapolate a bit. So if you're at the higher end of the range, so like if it's closer to a 2-inch bolt, then it's not unreasonable to use say the 0.7. But yeah, that's or you can just pick something in the middle there. Both of them are reasonable approximations. For the surface factor, is simpler. Instead of using this, we don't bother with that, because if we are using a good commercially purchased bolt, they've got good surfaces. So we can just go ahead and use the CS of 1. That's if we're using these values of KF. And this is basically the primary thing we're saying here, is that this kind of already builds the surface factor into these KFs, basically. So just to review, you're applying your load. It's going to go from a certain amount to a certain maximum. Typically speaking, we're talking unloaded to 0, but it may not always be the case. But regardless, yeah, we can break the, we can essentially break the load that's applied into kind of its amplitude, FEA, and then its mean component as well, FEM. And then based upon those applied, so basically the FEM, like the mean, essentially basically kind of just increases from the perspective of the bolt. That just kind of increases the initial tensioning a little bit, but you got to keep in mind that not all of that is going to make its way to the bolt. Some of it's going to some of it's going to be kind of carried by a reduction in the clamping. So we're worried about what's happening in the bolt. So again, as we apply a load, we're going to get some of it make its way to the bolt, some of it, and then some of it's going to make its way to the, be reducing the clamping strength. So we basically kind of need to break that up into figuring out what the amplitude of the force in the bolt is, and and then the mean of the force in the bolt is. So again, here's our initial tightening, and then we figure out what the maximum force in the bolt is using this calculation based upon the maximum value of the FE, and we can find out what the minimum force in the bolt is, again based upon this calculation, and typically speaking that's just going to be using a FE of 0. But if your load is varying from some other value to F max, then you plug that into there too. Find out what use those calculations to figure out what the minimum and maximum forces in the bolt are, and then from there you use that to figure out what the amplitude and the mean forces in the bolt are. So typically speaking, again for bolts, what we're going to be seeing is we're going to be seeing an FB that is a lot larger than, sorry, an FBM that is a lot larger than our FBA. Those can typically those could be calculated directly based upon our Fi and our combination of the KBs and our KCs if we have the knowing what our FE minimum is and our FE maximum is. So what we're typically going to be seeing is we're going to be seeing something like this. So we're going to be usually starting out here at our initial stress, like here, based upon the initial load. We're going to be loading it up. So we're going to be causing some sort of increase in the stress in the bolt. Now what you need to keep in mind is that, so we're going to be starting out with just, the initial load's going to be based upon kind of our proof strength here. Our initial tightening, and then as kind of as it's loaded up, we add some portion of mean strength and some portion of the amplitude. So we get a loading condition that looks like that. Sorry, didn't mean this to do that. Loading condition that looks like this. So what happens is, we kind of swiftly have a tendency to kind of shoot past our loading lines here. But we get into that situation that we talked about when we were talking shafts, where as it's loaded up, we're causing yielding in the material, which means we're inducing residual stresses. So basically, as we pull on it at its maximum strength, kind of at the root tip, we're getting this. We're getting kind of a gross yielding in this area. So here, let's so like. That's happening at each root tip. So we're at each of these, we're basically getting a tendency for that little area there to stretch out. But then when we deload it, the next time when we deload it, that we've caused some bulk yielding there. Sorry, not bulk yielding. We've caused some localized yielding there. So when we deload it, essentially, as the rest of the bolt kind of wants to contract back down because the load it's seeing is lower, this little bit of material in here, it's bigger than it used to be. So it's going to be resisting the tendency for the rest of the bolt to want to contract. So it's causing a residual compressive stress. And then the next time you load it up again, you need to load it up enough to overcome that residual compressive stress before you get to tension on at that area. So you've induced some sort of loading condition that causes localized yielding that helps you out. It decreases the tendency for the loading. It decreases. It increases the amount of load you need to apply in order to get back to a tensile state locally. So as a result, basically what happens here is it gets loaded up. It induces compressive stresses. And those compressive stresses, it induces compressive residual stresses, and those cause a decrease in those compressive stresses that are induced cause a decrease in the apparent mean. So basically what happens here is we kind of take this line, this actual loading line that we've got here, and we shift it over. And it basically kind of gets, the way it works is it gets shifted over until it gets to the point where you're intersecting the SN-SU line and your SY-SY line. So kind of the failure criteria is going to be the SBA max, where we get that intersection. So that SBA max is going to be it can be calculated based upon the known values for the strengths that we have. So our SN, our SU, the SN is there as well, our SU, and then of course the SY. So we can calculate that. and that's basically so that's going to be our maximum amplitude that we can apply to the bolt uh, before expecting failure. And then we take our actual design stress, which is just the amplitude of the force in the bolt that we see, again calculated based upon what we see going on here, and the combination of the stiffnesses of the bolt and the joint, and of course the area in the threads, and then that KF, and then of course we have to take the KF into account. So then our SBA design needs to be less than the SBA max divided by our factor of safety. Or another way to put it is that our factor of safety is going to be equal to this SBA max divided by our SBA design. And yeah, relatively simple calculation from there. So this over this gives us our safety factor. And then as long as the safety factor we calculate for the actual condition is greater than the safety factor that you're supposed to be designing for, then you're good to go. So let's do a quick example here. We got a joint, got 2 aluminum plates, and they are bolted together with 1/2-inch UNF grade 7 cold rolled bolts. So if the effective area of the joint is 12 times the corresponding effective area of the bolt, so that basically helps us find out what our KC and our KBs are. And the tightening load is the initial tightening is 90% of the proof load, and we apply a axial load between 0 and P, and as we do so we need to figure out what the maximum loading of P we can have here to still support infinite life for a safety factor of 1.3. So I'm going to go ahead, I'm going to open up OneNote here. I am going to screenshot that. And let's start with the stuff that's in this lecture, I guess. So first off, let's figure out what our SN is. So we're working with this. We need an SN equal to the SN prime CL CG CS CR. Having said, again, we weren't told anything about the CR, so let's assume it's 1. And the CS is also going to be 1 because we're working with a high quality bolt. So those both end up being 1. CL 0.9. CG based upon the size of the bolt. So it's a 1/2-inch bolt. So going back to here for a 1/2-inch bolt, we're working within this range. So let's go with 0.9 for. Let's go with 0.8 for that, I suppose. Right in the middle of that range. And then our SN prime is going to be based upon the grade of the bolt. So we could go back to the previous lecture. Let's see here. So we got the different classes of bolts that can be used. So we are working with a grade 7 bolt. So let's go ahead and just kind of we'll copy and paste those values there. Working with a grade 7 bolt. Oh, I guess, never mind, I didn't have the headers at top, so that's going to be useful. So let's just write that down. So proof load, let's get what values we need. We want the proof load, the yield strength, and the tensile strength. So the SY, SU, and SP. So start off, the one that we're going to use in this calculation, we need our SU because our SN prime is going to be half of our SU. SN prime is equal to half SU, which is equal to 0.5 times our SU, which is 133 KSI. So that means that we can calculate what our SN is. Our SN is going to be equal to 0.9 times 0.8 times 0.5 times 133. And that gives us 47.9 KSI. So I got our SN, got our SU is equal to 133 KSI. We've got our yield strength. Let's write that down. So 115 KSI. 115 KSI. And we're also going to need what our proof strength is. So our proof strength is 105 KSI. 105 KSI. So proof strength is 105 KSI, and we were told that it was tightened up initially to 90% of the proof load. So that means that the initial stress is equal to 0.9 of 105. So that'll be equal to 94.5 KSI. So that's the initial stress. What other things are we going to need to know about this? Well, first off, we're also going to need to know what our thread area is. So we got this chart here. We're working with a UNF. So it's got fine threads, half-inch bolt. Let me just double check. Yeah, half-inch UNF bolt. So we are working with a tensile stress area of 0.1599 inches squared. .1599 inches squared. So, what other stuff can we figure out based upon what values we've got here? So if we go back to Well, if we have the if we know what safety factor we're trying to apply, we're trying to go for, and we know that allows us to figure out that what basically what our allowable SBA would be, our SBA design. Because we also know the SBA max is, because we know everything that goes into the SBA max equation. We know our SN, we know our SU, we know our SY. So we know what our SBA max is. We also know what our initial stress load is, our SI. That was just 90% of the proof stress. What else don't we know here? So we don't yet know the KF. We can look up what that'll be. So let's just first let's figure out what our SBA max is. So our SBA max. So SBA max is based upon that equation. So SBA max is based upon our SN, so 47.9. All these are in KSI, so we know that KSI times KSI divided by KSI gives us KSI. So I'm just gonna, for the purposes of saving some writing, I'm gonna skip writing it out and just give you what the final one is. So 47.9 times 133 minus 115, all divided by 133 minus 47.9 KSI. So that's what our maximum allowable. Sorry, that's going to be our maximum amplitude of the stress level for infinite life. So basically, that's what we'd have for a situation of a safety factor of 1. So 47.9 times 133 minus 115 divided by 133 minus 47.9. I missed a bracket here, didn't I? There we go. So that gives us 10.1. 10.1 KSI is our maximum allowable amplitude. So we've got that. We need to know what our KF is. So again, we're just kind of looking it up on this table here. So we're working with an SEA grade of 7. So it's a high strength bolt. So it'll be 4 and above. It does specify here it was a cold rolled bolt, so it wasn't a cut bolt. So we are looking at, we're in the rolled threads column, and we're in the high strength row, so we're looking at 3.0. I'll just write that down. Right down here. KF is equal to 3.0. Okay, so going back down to here, what's the other thing? Let's see. So the only unknown that we have here really is the force in the bolt. Sorry, the amplitude of the force in the bolt. So we know what our AT is. We know what our KF is. we don't yet know what this force is. We can figure out what our SBA, what our maximum SBA would be, just based upon this equation here. So if we solve for our SBA design, then that'll give us kind of the maximum value we can use for that. So that's our SBA design is just, or the maximum value of our SBA design in order to meet the factor of safety we're looking for is just the SBA max divided by the factor of safety. So we're looking for a factor of safety of 1.3. If our SBA max is 10.1, then that divided by 1.3, SBA design max, I'm going to put max there, is equal to 7.8 KSI. So that's the maximum allowable SBA that we could have in order to still meet our failure, our safety factor. And of course, that is just equal to our KF times the FBA divided by AT. So we can solve for what FBA is based upon that. So our FBA FBA is equal to the SBA, 7.8 KSI, times the AT, so AT of 0.1599 inches squared, all divided by the stress concentration factor of 3.0. So yeah, solve for this, just multiply out by the AT divided by the KF. So 7.8 times 0.1599 divided by 3.0, that gives us an FBA of 415 pounds. So as, of course, when I'm multiplying this out, the KSI, that's 1,000 pounds per square inch. The inches squared cancels out. So punching this directly into the calculator will give us a value that's in thousands of pounds. And then it was 0.415. So anyways, 415 pounds is what our FBA is. So maximum allowable FBA in order to still meet our design criteria. So we know what our FBA is. So the next thing we're going to need to do is kind of figure out, we know what our FBA is, so that's the maximum amount of force of the load that can get to the bolt, which isn't, so we need to kind of translate the applied force to that. So that depends upon our stiffnesses, right? So if we go back to here, let's see here. Just keeping in mind that our FB in general is going to be the initial load plus the applied load times KB divided by KB plus KC. Now, if we're looking for the amplitude, that's just the variation. So instantly, we toss out the FI because that doesn't come into play for the amplitude. The initial load, the initial load affects the mean stress only. It does not affect the amplitude of the stress because it's constant. So our FB is our FBA is going to be equal to FEA times KB divided by KB plus KC. Now, in this instance, we are working with an FE that varies from 0 to some load P. So in that case, our FEA is equal to P over 2. Because, we're going from 0 to something, then back down to 0. So our average and our mean, our mean and our amplitude there are both half the maximum load. So our FBA is equal to P over 2 times KB over KC plus KB. So if we want to use these equations to solve for what the P, what our maximum P is, then we need to figure out what that ratio of those stiffnesses are, the KB over KC plus KB. Fortunately, so what we were told is we were told what the ratio between the effective areas are. So we can use that. So we know that KB is equal to the area of the bolt times the Young's modulus of the bolt divided by the grip there. I'll just put that there, and then for the joint, we got that. So what I want to do is I want to figure out what KC is in terms of KB. So what we can do here, we know that we can take, we know that in this instance, the AC is equal to 12 AB. And we can also, the other thing that we know is what the stiffness values are here, the EB and the EC. So we can look those up. So I'm going to go ahead and let's go ahead and open up juveniles here, just to double check what the stiffness of those two materials are. So let's see here. Let's go for Appendix C1. I'll rotate that so we can read it. And we're looking for what here? We're looking for the modulus elasticity. We're looking for the modulus of elasticity for steel, and we're looking for the modulus of elasticity for aluminum. Because that's the two materials that we're working with. It's two aluminum plates bolted together for the EC, and it is a steel bolt for the EB. So the modulus of elasticity for the steel is 30 KSI, or 30 mega PSI. 30,000 KSI, 30 mega PSI. and the modulus elasticity for the aluminum. Again, it has more of a tendency to vary, but again, they didn't specify, so just pick a representative value. The one that's in the chart works. 10.4 megapascal. Not megapascals. Mega pounds per square inch. So if we want to figure out what our KB is, if you want to figure out what this kind of ratio here is, we are just working with AB times 30 times 10. Yeah, here, I'll put MSI here. Divided by G. And all of that over, same thing, AB times 30 MSI over G plus KC. I guess I did it, so I did the KB one first instead of the KC one, but anyways. So the AC, I'm going to just pump in there. We know that the AC is 30 AB. Sorry, 12 AB. 12 AB times the EC. So the EC there is 10.4 MSI. I'll divide by G. So everything here is divided by G, so we can just, we can, on both the top and the bottom, so we can just cancel out the divided by G's. And everything here is multiplied by AB, so we can cancel out the AB's. And everything here is that's left is in units of MSI. So let's just cancel out the MSI's. And we're left with a nice dimensionless ratio. So we have 30 divided by 30 plus 12 times 10.4. That gives us a KB over KC plus KB ratio of 1.93. 1.94. We're under 1.94. So our FB is equal to P over 2 times 1, sorry, 0.1, did I say 1.94? Sorry, my bad. I'm reading off the calculator wrong because I often say numbers wrong. My bad. 0.194. 0.194. So that is what our FB, that was supposed to be our FBA. That's our FBA because we already took into account the fact that the load is its amplitude portion by dividing by 2. It's also the mean, this would also be what the mean is, but anyways. So that's our FBA, and that's kind of the load side of the equation. The strength side of the equation is up here. So our maximum FBA is equal to the 415 pounds. So 415 pounds is equal to P over 2 times 0.194. So therefore, the maximum P that we could use for that varying load is 415 times 2 divided by 0.194. So that'll be 4.3 kips. Well, 4.28 kips. Let's go with that. Don't want to be too aggressive with the rounding. So yeah, that is the answer to the maximum amount, the maximum loading P that this joint can support for infinite life when you're loading it up from 0 to P. Second step here, we also want to verify that the clamping load is adequate. So basically we want to make sure that when that load is applied, we still have some clamping going on. So again, that is basically let's see, where do we have that formula here? So in that instance, we need to make sure that the FE is still less than the FI times KB plus KC divided by KC. So I suppose we need to figure out what the initial load is, the FI. We know what the initial proof strength was, the initial stress was. We never went ahead and calculated that in terms of initial tightening. So we would do that by taking our SI here and just multiplying it by the AT. So 94.5 thousand pounds per square inch times 0.1599 square inches gives us 15.1 kips is our FI. FI is equal to 15.1 kip. And then got this ratio here. So again, same idea for the calculation, except you got the KC term on, it's mixing it up a little bit. So we'll just kind of recalculate that. So the KB, I'll ignore the divided by G ones. We know that's going to be canceling out. In fact, I'll just throw the numbers down because we already saw how the units cancel out. So when we're looking at KB 30 plus KC 10.4 times 12. So again, this is 1 AB plus the 12 AB, and then there's going to be a 12. There's going to be an AB on the bottom. So I'm just kind of preemptively canceling that out for the purposes of decluttering this a little bit. And then the KC 10.4 times 12. So this ratio ends up being 1.24. So our FE needs to be less than our FI times 1.24. Needs to be less than 18.7 kips. Given that in this instance our P, the load that's applied, is 4.28 kips, that's significantly less than the 18.7 kips, which would cause opening of the joint. So the clamping load remains accurate. Remains adequate while we're still loading up here. So that's good. And that's about that.